So after this discussion, which is a bit theoretical, I'm going to go to a practical experience. So I'd like to give you feedback on what was my first real exercise of porting, of instrumenting a code. I've taken one given solver and I've used 3 different environments to interface with a visualization package. The first one was to use ParaView-Catalyst, but what I will describe here is actually the new Catalyst. As of version 5.9 of ParaView, there's a completely different way of interfacing ParaView-Catalyst to a simulation, and this is something that is new. This is something that I thought would really poke your interest. Second method I used, excuse me, is to interface the same simulation with Ascent, and we will talk about Ascent in great details. And then the third solution, which is a hybrid solution, uses the data description that is created for the ParaView-Catalyst, feed that to Ascent, and have Ascent read and execute ParaView Python scripts. And we will see that this is also quite an attractive solution. So I'd like to advertise this solution. So let's look a little bit at the different components that are required here. I don't know how much I need to present ParaView because it's such a well-known system, and as Anne recorded earlier at the beginning of the presentation, I was at Pawsey a couple of summers ago to present ParaView in great detail. So ParaView, in a few words, an open source multi-platform application developed by Kitware, and ParaView really can run in at least 4 different scenarios on the desktop, and it's multi-platform, so Linux, Windows, Mac, you have it, it's there. It can run in client-server mode, and the important thing here is that your client remains a very lightweight desktop application, and all the heavy parallel execution of visualization filters is done on the server side, for example, your supercomputer. ParaView can run in batch mode with Python-driven scripts, and those Python scripts are actually very intuitive to read and edit, and that makes it for a very simple interface. And then ParaView can also run in-situ when coupled with your simulation codes. And for in-situ scripts, there are actually the same Python scripts which we use in batch mode with a few minor modifications. Then there's the Catalyst part. Catalyst at this time is really an API specification. Okay, so it includes a lightweight implementation of the API, and it has a stub library, very lightweight, which means that you can start developing your simulation code with the Catalyst API. You can link to that library, and there will be no runtime cost while you do your early deployment, because that library is really a no-op operation. And then you can switch to the SDK, the ParaView SDK, which will provide the full implementation of the API. The next component that we will need to use is Conduit. Conduit is really a lovely package I have discovered while doing this exercise. Conduit is an open source project from Lawrence Livermore. which gives a very intuitive model for hierarchical scientific data in all the major languages we know, C, C++, Fortran, Python. So I've put links to all the different sites here. If we click on that particular page here, it would go straight to the Read the Docs Conduit page. And what is important here is to find out that those two particular components of Conduit, a JSON-inspired data model, so very easy to describe hierarchical in-core scientific data, and an API that gives a dynamic API for rapid construction and consumption of hierarchical objects. So we will see through the tutorial how easy and how intuitive it is to describe data using Conduit. More on this in a little bit of time with examples. Now, Conduit is about describing a set of hierarchical data. But really, we can describe anything with it. It's just like using in HDF5. HDF5 is an API, and I could store my data in any way I want using the HDF5 API. However, if I expect my visualization code to read my HDF5 data back, I need a convention. The same is true with NetCDF. And if some of you are in the meteorology and climate community, you would of course know the CF conventions, which are a conventions to describe computational data related to meteorology and climatology. And if people use that NetCDF CF convention, then the visualization software can read them transparently. So the same is true with Conduit. Conduit provides a convention to describe computational simulation mesh. I could use Conduit for any other purposes, but if I want to describe computational data, I'd rather use the mesh blueprint, which is the name of this convention, because the mesh blueprint really is a set of conventions to describe the data such that we can feed the data both to Ascent and to ParaView for an in-situ visualization setup. So I'm going on the mesh blueprint web page here. I'm going to look for the keyword required. Okay, and we will see that there's only really two objects that are required to define a computational mesh using Conduit. It's the coordinate set, and as you would expect, the common set of coordinates are supported by Conduit, the Cartesian, cylindrical, and spherical coordinate set. And then the next required object is the topology. The topology would be about here the set of elements which form your computational mesh. And here it's pretty intuitive. The different geometric types which are implemented in Conduit go from the point to the line to the triangle to the polyhedron. And that's really the only two required objects in a Conduit definition of a mesh. Then, of course, we can add data associated with the mesh, and we will see how this is done later on. We have a number of illustrations of the mesh blueprint. So, for example, the basic object, the basic mesh generation example from the Conduit blueprint would take as arguments a mesh type, which can be uniform, rectilinear, structured, etc. And if I look at the illustration of those different examples, I would see, for example, here, the uniform coordinate set of size 3 by 3 with a given origin, a given spacing, and one solution field called field, in fact, which is stored at the element and has value 0, 1, 2, 3. So 0, 1, 2, and 3 are the scalar field associated with this particular mesh. And we will see how trivial it is later on with the Jupyter Lab example, how trivial it is to generate such configuration. The same example we have with rectilinear, where here in the rectilinear case, we have to explicitly give the x coordinate, or rather the coordinate for the x-axis and the coordinate for the y-axis. And then in the structured, or some people call them also curvilinear grids, in the structured grid case, we give an explicit list of coordinates for all nodes on the mesh. So there are some illustrations of the mesh blueprint. We can look here at the triangular mesh, the quad mesh, and so forth. So the great thing about this is that the Catalyst API uses Conduit for describing data. And we will see how this is done. So let's look at the first example of Conduit. I'm going to switch to my laptop here. But the great thing is that actually those examples are also available via a Docker container, which you can run directly on your machine if you have Docker installed. So I'm going to drive you through that particular example, but you will be able to repeat that on your own desktop as you try. Let me switch over here. Just give me a second. Actually, I think I have that Jupyter page, the Jupyter Lab notebook already loaded. So there is Conduit. I assume here that everybody is familiar with Jupyter Lab, but if not, you will see that in any case, it's something very intuitive here. So I'm going in Python to import my Conduit node, and I'm also importing NumPy, because you will see how the NumPy arrays are directly serve as the data containers for the Conduit data descriptions. So I'm importing those two packages. And really, here in the second cell, I'm creating a Conduit node with a particular key and a particular value. And when I print that node, I have my key. I have associated to that particular key a value. In that case, this is a string value called value. And that's all there is to it. We have here a Conduit node. In the next cell, I have here a description where the key is interesting because the key is already a hierarchical path, dir1 / dir2 / value1. And we can construct the node directly as it is because it imposes a tree structure on the particular Conduit node. So if I execute my cell here, I directly have this hierarchical description all the way to the leaf of the node, which has a key called value1 and a numerical value of 100.5. There, I think you have all become experts in Conduit in 1 minute here. You know how to import Conduit, you know how to construct a node, and you know how to construct a hierarchical path for the associative array. That's almost all of the story. And then we need to attach data to the node. So this is where the NumPy array would come in. In the next example here, I'm going to create a Conduit node. I'm going to create a NumPy array of size 10 with 10 different integers. I'm going to fill up those 10 integers with a Fibonacci suite. I'll give it the key fib, and I would set the array A as my data. And there is my Conduit node. The access key is fib, and the NumPy array is over here. Now, in terms of in-situ visualization, and in terms of shallow copy and deep copy, this is where Conduit will show all of its strength. I'm going to show you two different ways of giving NumPy arrays to a Conduit node. So in the very first part of this cell here, I have the standard setup for the Conduit node. I'm going to create a second copy of an array called A2, which I will fill up with exactly the same values. This is the Fibonacci suite of integers. And for one of them, one of the Conduit node, I'm going to use the set command or the set external command. And one of them, as you can see from the associated key that is used to address the node, one of them is the shallow copy. So set external is a shallow copy. Indeed, if I modify the last element addressed by -1 of the array A2, if I modify this, I will modify the value that is held by the Conduit node. If instead I modify the value of array A1, but that array was deep copied, the Conduit node will not have that updated value. Indeed, we can verify when we execute the cell that we have, in one case, a deep copy of the array, and in the second case, a shallow copy of the array. So this mechanism is going to be what we use to describe our computational mesh using Conduit. We're going to create a definition using the required keyword of the mesh blueprint and using as much as possible those shallow copy of data using the memory pointers in our simulation to describe our data, and the in-situ and the visualization package which supports the mesh blueprint using Conduit will be able to read the data and access the data exactly in that fashion. That's basically all there is to using Conduit. So let's see how I've done this with Catalyst. Now, in the past few years, which means before version 5.9, Catalyst had a VTK-based API, which means that we were forced to write a data adapter using the VTK API. So we needed the understanding of VTK mesh types, data types. We needed to understand how VTK implements data sharing, shallow copies, deep copies, all those things. And really, this was a pretty difficult operation for somebody who's not intimate with visualization software and with the VTK library. So certainly not for a simulation code developer without more than just a basic understanding of the VTK software. So this was I dare say the past, because it's still supported in the upcoming ParaView 5.10 version. But this was really a heavy development effort because it required the understanding of the VTK implementations of data meshes. In contrast, the Conduit-based API, so from version 5.9 and onwards, and I'm currently using version 5.10, release candidate 2 of ParaView. Writing the adapter requires the basic knowledge of Conduit, which we've done in the last 3 minutes here, to be able to interface code using Catalyst. So this is what I'm going to give more details about. In ParaView 5.9, the Catalyst API will use a Conduit for the data description of a simulation code. So for the rest of the discussion this morning, I will assume ParaView 5.9 plus and the Conduit-based API. And you will be surprised at how easy it is to interface simulations code to Catalyst. Now, in addition to the mesh blueprint, which is this set of conventions that Conduit has to describe computational mesh, ParaView also uses Conduit for the so-called ParaView-Catalyst blueprint. Because there is a little bit more than describing the mesh itself. We also need to tell Catalyst the name of channels where data will be available. We need to be able to tell Catalyst where to find the shared library for the Catalyst implementation, where to find Python scripts to load, and this is implemented with the ParaView-Catalyst blueprint. But we shouldn't be afraid of that. You'll see again that it's just a couple of keywords here and there. Now, to set up our visualization using Catalyst, several ingredients will make our interface task much easier. The first one are the so-called ParaView extractors. Extractors are objects which we find in the visualization pipeline, and they can save images or data to disk. So for example, if I have a three-dimensional computational grid, and if I compute an isosurface, that isosurface can be saved to disk via a data extractor. And then if I have multiple views, I can save any of those views to images using an image extractors. So the names maybe sounds like some pretty heavy duty thing, but it's actually something very simple to use. And it makes it such that we, in most cases, we can take an existing ParaView Python script, add a few extractors to it, and feed that to the in-situ setup to get our visualization done on the fly. So more examples on that, more details on that in a bit. The ParaView-Catalyst Python script is something that the application itself, ParaView, will write for you. Now, usually, this is how we operate. We take a representative template file on disk of what our simulation is going to produce. So, for example, you run your simulation at a lower spatial resolution, which you can afford to save to disk. You save to disk one sample of data. You read it with ParaView. You fine-tune your visualization. You set up all the different parameters and filters and queries that you wish to do. And once you are ready, happy with your visualization, you ask ParaView to save the corresponding Python script to disk. That Python script can then be complemented with a few of those extractors to save data and images to disk, and you have there at disposal a Python script that is ready to run in situ. Now, recall that ParaView provides actually a pretty extensive set of parallelism out of the box. MPI enabled, TBB multi-threading, OpenMP, CUDA enabled filters. So all of this power is available to you for executions given a standard Python script. So this makes it really simple to develop. All right, so let's look at a couple of examples of Python here and how I would operate, how I would design my visualization. As I said, I would start from an example representative of what the simulation will do, of course, at high resolution, and I read that data file. So this is the first line of my Python script here. I open that data file and I call it grid, and this is something that will be very important for us. This keyword is what we will see in the Conduit mesh description, such that ParaView understand that the Conduit node referred to by the name grid is actually the data we want to visualize. The most trivial Python ParaView pipeline that we can imagine is the creation of a view, a standard three-dimensional view, and then we show the object, which is the current object, meaning the grid. We show this object, which means we create a graphical representation of it. And we color this representation by a field. For example, here, I take the velocity field and I want to color each point of that mesh with the velocity field. And the last command to execute is the render command. So here is the basic, the elementary Python code I need to visualize the velocity field from my grid of points. If I add some extractors to it and I execute in batch mode, with this particular import, I can save all my extract using the catalyst options which are defined by ParaView. This is on the left side of my screen, the Python script which ParaView would read both in an interactive session and also in batch mode. If I look now on the right side of my screen, this is what ParaView would execute in situ. I would replace, of course, I'm not reading data anymore from disk, but I'm reading data from memory. And it has the same name, this grid name, such that via the conduit node description, ParaView will recognize that the data that sits in memory is the same data. I would again create a view, show my data, color it by velocity, and with an extractor, which is triggered based on the time step at a frequency of 30, I would write my data. And here, as you can see, there's no loop over the different time step of my simulation. And that's what makes those extractors very simple to use. The catalyst engine behind is what is responsible for doing the looping, and is responsible for saying 1 every 30 iteration of the simulation code, I want to execute that pipeline and save data to disk. All right, so I've talked about the blueprint, the ParaView-Catalyst blueprint. It's a protocol with 3 different functions, very simple, very trivial. And I will tell you how trivial it is in terms of how many lines of code I had to write for the interface. There's the initialize subroutine call, the execute code, which happens at every iteration of your simulation, and then the finalize code. So the blueprint that is used for ParaView-Catalyst is very similar to the Conduit mesh blueprint. I have here a hierarchical key for a Conduit node. So under the Catalyst heading, under the script sub directory, if you wish, I have the file name here for the Python script to execute. Under the Catalyst state subkey, I have both the time of iteration and the iteration number. And then here comes the grid keyword, which I told you to be aware of. Under the different channels of input of Catalyst, I am informing ParaView that the grid object is what I will need to refer to as my mesh. So it's really, the principle is really to understand that you connect your ParaView-Catalyst blueprint definition with the same key to associate your data in memory as described by the Conduit mesh blueprint. We will look at the practical example here in a second. So there's the practical example. I've instrumented an SPH solver with ParaView-Catalyst. SPH is a technique which uses a purely Lagrangian method. It discretizes a set of fluids with a series of interpolating points. I will call them particles. And those points follow the mass density of the fluid. Now, as part of PASC, the Swiss Platform for Advanced Scientific Computing Initiative, supported by the Federal Council of Switzerland, SPH EXA is a project which implements the SPH technique for use in astrophysics and similar problems. And SPH exa supports parallelism in different forms: MPI, OpenMP, CUDA, and HEAP. So we started instrumenting the SPH exa application with Catalyst. And here's the effort that was required. Using Conduit, a particle set is really trivially described. So on the left side of my screen here, I have the first required element for a particle set, which is the coordinate set. Here I have a standard toy example with 4 particles, X, Y, and Z coordinates, and that's what I need for my coordinate sets. The C++ code, which I used for the ParaView interface, has the following parameters. Here again, the description of the channel, the input channel, referenced by the keyword green. The type of mesh is mesh in that case, and the data has the following coordinate set: an X, a Y, and a Z and a Z coordinate, which are shallow copy of my simulation pointers X, Y, and Z. So here I am describing the complete coordinate set of my simulation data with those 3 shallow copy links defined by the Conduit node. The second required object in Conduit is the topology. So for a particle set, the topology is of type unstructured. The shape of the element is point, and the connectivity here for 4 particles would be 0, 1, 2, 3. Well, in the case of my simulation data, where I have n particles, the corresponding C++ code on the right side of my screen would be an array of size n for the n particles. It's a standard vector, which I fill up with the series 0 to n minus 1. And I set again the connectivity of my array with the name, the pointer in memory for that particular array. And then finally, I add the different solution field, the different scalar and vector field associated with my solution. So for my toy data set, I would have under the fields a keyword, I would have the name of my variable. The association would be vertex, and the values would be, for the toy example, -1, -2, -3, -4. For the real code, using the fields string key for my Conduit node, I would set my density scalar field to be called row. And again, I would give a shallow copy. I would give the address of the pointer in memory, in the memory space of my simulation, as a shallow copy for the values array. And that's all there is to it. Now, just to debug things, Conduit has also an interface called the relay protocol, where I can save data to disk. So given the toy example I had here on the left side of my screen, I could very simply, in Python here, if HJ5 has been compiled into the Conduit installation, I can save my data to an HJ5 dataset. And those of you familiar with the HJ5 format, if you do an H5LS recursive of my dataset, I would have a group, a hierarchy of group, and then the data sets for the type and values of my coordinate set. For each of my solution scalar field and vector field under the group fields, I would have the particular data set, and so forth and so on, also for the topology. Now, I just said if HDF5 is compiled into your installation of Conduit. So how is Conduit installed? And that's probably something you'd like to know if you want to run some of those examples and get to know Conduit. Conduit can be installed on your system via SPAC. So I would recommend that. And if that fails, you can actually do a manual compilation of Conduit. I had to do this on our Cray at the moment, but otherwise it's very well documented on the Conduit web pages. So you can most likely install Conduit and Ascent very easily on your own computer. There we go. All right, so in total, and that's the good news, the Catalyst glue code for the SPH Exa solver is 144 lines of code. So those 144 lines, that's basically the definition of the mesh in memory using the Conduit mesh blueprint. And then enabling in-situ visualization can be optionally compiled. So this would be on the right side of my screen, the original code. I do an MPI init, and then I run my solver for a number of iterations until I finish. And then with conditional compilation, I can include my adapter, which are those 144 lines of code. I initialize my adapter, and at each of my iteration, I execute my Catalyst adapter. Let me check on the questions here. So does Conduit care about the HDF5 API? I'm not sure I understand the question here. I guess what you are hinting to is what is the level of the API, and I think I had to use version 1.18. I'm confusing things here.
So I checked on the SPAC recipe, at least says 1.8.x, so it would be the 1.8 API.
Oh yeah, exactly.
But okay, so if that's the case, that's great. We'll just curious. I want to try to install this, so I was gonna get it up and running.
I think if I recall, I had to use one compilation flag because on the Cray I had a 1.10 or 1.12. I'm now confused. But just by setting the API level to 1.8, I got it to compile without any trouble. So please, if you're installing this on the Cray, for example, and on the Cray I had some difficulty installing, I created a manual recipe which works really out of the box, and I set that API level at that time in one of the flags. All right, so that's it. So with 148 lines of code, I interfaced SPH Exa to Catalyst, and here's the one screenshot of the simulation. I will actually show you now the video. It's nothing very exciting at the moment. This is a standard set of blast explosion. The thing to see in that visualization, if I pause there we go, is that I don't have the full set of particles here. The full set of particles actually fills up the complete domain here of this cube. But I'm only showing the particles at a given density. And I'm going to explain now how I did this. That's the title of my next slide. What about operations control? We've talked early this morning about adaptive control. Choose different path of execution based on a particular query or triggers. Well, this is very simply done via the catalyst execute. This is one of the 3 API calls of the Conduit setup. In my catalyst execute, I pass the Conduit node description. For example, this node description gives me access to the time step, okay? And given a particular threshold, which was set at 1.4 for this example, I test, I do my query. If the range of data for the density scalar field of my data producer is greater than threshold, then I extract the particles where density is greater. Else, I use all particles. So this is what I did. So basically, this adaptive control can be done sometimes in just a few lines of code. You will add your query, and then you will do different things. So this is basically modifying your ParaView pipeline to tell it to execute different things in terms of the data ranges which you have. Okay, next slide. What about operations control? Human in the loop. Now, ParaView has a very efficient client-server mode. It uses a remote server, as we've talked about, with parallel parallel filtering, parallel image composition, and it uses a very efficient image delivery engine, which means that the results of your visualization pipeline stay on the server, and the only thing that gets transferred over the network to the client is the image. So for example, a 1024 square pixel image, and that's very lightweight as compared to the data that sits on the server. So ParaView-Catalyst will use exactly the same engine. I will open a port from my desktop here at home to the supercomputer at CSCS. So pitch daint is the name of my logging node. I open a reverse terminal to my desktop. And then I tell my ParaView client, using those 4 lines of Python code, to enable Catalyst Live and to look for a call on that particular address, the host name, and the particular port. And I'm going now to show you a video that I made demonstrating this, this connection. So here's the setup. Sorry, I need to start at the beginning. There we go. Here's the setup. On my desktop, I open a reverse SSH channel to the logging node. My compute job is already running, so it's waiting for connection. I launch my ParaView desktop on my, and I ask Catalyst to connect. And what happens here is that immediately the pipeline browser is filled up with the full pipeline, which was specified by my ParaView Python script. And in a matter of seconds, I have here a live connection to my data. what it perhaps went too fast, but I forgot to tell you that I actually paused the simulation for that particular exercise. So any of the elements which I see here on the catalyst category of filters, those are the filters that run in situ while the simulation is running. And then I can selectively place those elements on the built-in side over here, which is at the top of my pipeline browser, and I make those elements visible on my client. So this is what I've done. And at this point in time, so here's the set of particles with, at this point in time, I can select any of the ParaView filters available on my client to do further visualization and analysis of my data. So here I'm setting up an SPH plane interpolator, which will enable me to reconstruct a planar cut through this particle point cloud. So I've taken some shortcuts. It takes a few seconds of execution, but there is now the reconstruction of my point cloud through the field. So this is really the ability of having a set. Sorry, I wanted to pause at the right time here to demonstrate to you that after a while, there we go, I go to the Catalyst menu and I give control back to the solver. So I tell the solver, we can continue execution. All right, so we've seen how Catalyst Live can now interact with a running simulation by interrupting the simulation, making any object from the pipeline visible on the desktop side, and giving us the ability to add additional visualization components to the live data. And once I'm done with it, I can close, I can give the control back to the simulation. I can disconnect, and I did the experiment last week. I could disconnect, I could go eat lunch, come back, reconnect to my simulation, and get some newer data. So that worked pretty robustly. There are other examples. For example, Lulesh, which is one of the proxy apps from ASC, has been instrumented for ParaView-Catalyst. And I recommend that you look at the earlier version of Catalyst at this address. This would be the instrumentation using a VTK data adapter. And you would see how much effort is required. And then the new interface with Conduit is also available at this address, thanks to Utkarsh. So I recommend, if you are interested in looking at the old versus the new interface, you look at this particular example. Now, for my second method, Ascent, we will see how we do things. So what is Ascent? Ascent is another library created by Lawrence Livermore with a focus on, again, on efficient distributed memory, MPI many core, with demonstrated scaling, in situ filtering and ray tracing was done on over thousands of GPUs on Lawrence Livermore Sierra cluster. And the great thing about Ascent, and we will see the example here in a minute, is that it it is based on Conduit. So the definition of the data and the definition of the visualization pipeline is all done through the Conduit API interface. So that makes it also very simple and very intuitive to operate. I will look through a couple of slides of the Ascent tutorial from the Ascent tutorial, because I think they are absolutely worth our time. Let me go to the full web here. So this was the part of the tutorial given by Cyrus, Matt, and Hank Childs. And I want to point out that all this tutorial is available on the website of Ascent, the docs, etc. All right, so you can run the tutorials through Docker over here at this address, or else if you have an installation of Ascent, as I do here, you can run those Jupyter Lab notebooks directly on your laptop, and this is what I will do in a minute. So Ascent can, of course, do all the standard visualization analysis that we are familiar with, making pictures, transforming data, capturing data, all this through the standard APIs of C++, C, Python, and Fortran. So that's quite interesting. Ascent is also available via SPAC, so that should ease the deployment on your particular infrastructure. And like I mentioned, Ascent is ready to use for the normal visualization use case that we are all familiar with. All right. I'll let you look at those slides in a more tranquil setting, because they are extremely well done and very easy to follow. I want to go to one particular set of slides, which is about a tutorial, which is where you will learn how to use Ascent. And I will show you exactly, and I will discuss just discuss this particular slide, which talks about the 5 top-level functions which Ascent expect in your code. So the open and close calls that I guess are pretty intuitive. The publish code, which is passing your data to Ascent via the Conduit node description. And then the execute call, which actually runs your visualization pipeline. I think we will, for the interest of time, I will go to my particular showcase. So Ascent, as mentioned already, is based on the Conduit mesh blueprint. So all the efforts that we have done earlier with the Catalyst API can be reused, recycled to use Ascent. The next component of Ascent is the runtime. So the analysis, the rendering, and the I/O. And as I mentioned already, this is also prescribed by Conduit nodes, and I will show you a couple of examples of that. And then the data adapters, and that's the good news. Just like in the case of Catalyst, the data adapters are now internal to the Ascent implementation. So you do not have to worry anymore. You do not have to worry anymore about the shape of the data objects that are sent to Ascent or Catalyst, the data adapters are embedded into the API. I will run from my laptop this particular JupyterLab notebook, but recall that those are available also in the tutorial. So if I go over here, there's the Ascent tutorial, the Ascent notebook. Very first page should be familiar to us. We import Conduit and the Conduit blueprint, and then we import Ascent. In our second cell, we build one of the example mesh from the blueprint, and this is a mesh made of hexahedra of resolutions 50 by 50 by 50. There we go. And this is where the Ascent pipeline is defined. We create an Ascent node. We open the node with our predefined options. We publish our mesh. And then we need to create at least the bare bone of a scene. And the bare bone of a scene in that case is just a simple pseudo color plot of the mesh. So you are now familiar with the syntax of Conduit. We had a particular action, which is a scene. We define a particular plot of type pseudo-color. For the variable name of the field, we use the variable called grade. And then to save the image, we give it a file name. And once we're done with it, we execute our action. So let's do this. I have printed here to the screen my action. And as you can see, we have a pretty well-defined pipeline, a scene called S1 with a single plot called P1 of type pseudo-color with a variable called bread and a file name called art first light on 3D. And through Jupyter, Ascent has a viewer for that particular Ascent node, and here's our mesh. Okay, so there's nothing else to it. It's really given a mesh definition, which we did here in cell number 2. This is a Conduit node using the blueprint. Given an Ascent node definition with a scene, we get our image. All right, I'll move forward with the third example, which is to use a little bit more, to introduce a few more ideas from Ascent. So again, I will import Conduit and Ascent. And I will create here a mesh using Conduit of type uniform with a given resolution of 9 by 9 by 9. And I will set a scalar field over here under the fields substructure. I will give that scalar field the name alternating, and I will set the values via shallow copy. I will set the values of that particular field to the array constructed here above. So this will be a set of alternating values between 0 and 1. if I execute this cell and then print my mesh, as you can see, we have the required coordinate sets, the required topology, and then the optional scalar field called alternating with the following values. Now, since the blueprint is a convention to use to describe meshes, we have a verify command to make sure that we construct the conduit node in the appropriate fashion. So you are welcome to verify that your node actually conforms to the blueprint. We do this, and then we create our pipeline. Up to here, things are like in the previous example, we haven't changed anything. And we have an alternating value between 0 and 1. Look, for the interest of time, I'm going to skip the rest of those examples, which you can redo at home, and I will show you how to instrument, or I have instrumented the SPH exa simulation package with Ascent. So the first thing was to provide the conduit mesh node definition, which I reused from the ParaView-Catalyst code. And then I add a basic scene definition. In total, and that's the good news again, I have about 100 lines of code to interface SPH exa with Ascent. In the basic form of the Ascent instrumentation, I have a hardwired default scene description. And that scene really is take the points, render them, and make an image. Now, with Ascent, at one time, I can supply different visualization pipelines. And the way this is done is with a file, a JSON file called Ascent actions, which is read at one time and which overrides the basic template definition of the scene. So let me go through that example. I have again a scene with a pseudo color called with the field density. I can set up my camera, as you can see here, with a particular position and look at points. I can add, again, add a pipeline which will do the same threshold operation I did with ParaView-Catalyst. So there's the pipeline definition, a threshold, which takes a minimum value of 1.4 and a name for the density field. And what is important is the name of this pipeline. This particular visualization pipeline is called PL1. And in my scene definition, I will modify the plot to say I want to plot the pseudo color of points, but before I do this, I want to apply the pipeline PL1. And that's all there is to the definition of my visualization pipeline. So I can compare the ParaView pipeline for Catalyst, which created a view, selected points with a particular query string here, density greater than 4, extracted my selection, and saved the image to disk using the creator. I can compare that to the definition of the Ascent pipeline on the right side of my screen with a threshold definition for the pipeline, a scene definition which takes into account, I'm sorry, right here, the pipeline PL1, and then a render definition which takes a particular image prefix. I will conclude in about 2 more slides here, so please bear with me. My third method is to use Ascent and reuse ParaView Python script. Since I have the ability to specify at runtime the visualization pipeline which I want to execute, I can also tell Ascent to read a Python script provided by ParaView, because the point is that both Ascent and Catalyst share the Conduit blueprint mesh specification. So they know, they are aware of the same data in memory. That data is described by the Conduit blueprint. And then the way this is implemented in Ascent is via a ParaView plugin, which will construct data of type image data, rectilinear, structured or unstructured grid. And that plugin will internally convert your data to the VTK format, which is required by the ParaView script. So this would be my action node defined for Ascent. I will tell Ascent to add a particular extract of a particular type, and this type is Python, and I will tell Ascent, please read the file called ParaView-Vis.python. And this ParaView-Vis.python is a script from the standard ParaView pipeline environment. So in summary, what I've done is I've completed my first early adopter phase for two environments, ParaView-Catalyst and Ascent, which share a conduit-based description for the mesh. As we've seen in the examples, the conduit mesh is something very intuitive, very simple to set up. And we've seen with, of course, an SPH solver is a little bit simpler. Sorry, is a little bit simpler to use because we only have particles without a mesh structure, but we should be able to adapt that to any mesh-based simulation. The Lulesh example, which I have given you reference to, is one such example. Now, the moral of the story here is that both ParaView and Ascent provide bridges to your data, hiding all the complexity of the previous developments which required people to have expertise in building data adapters. So that's the real neat thing about those developments. Both environments have proven tracks of high-scale deployments. So my next step now is actually to evaluate on different codes, evaluate the performance, and especially the memory consumption of an in-situ deployment using those two different solutions. So for the first time in quite a long time, I can now forget about developing data interfaces to visualization packages, and I can concentrate on the aspect which I am a specialist of, which is really visualization. Now, back in 2011, I recall when I was presenting Lipsyn, people would tell me, we don't have enough memory. We are already so tight on memory, we cannot afford to have an in-situ implementation consuming memory from our code. So this is perhaps a motivation, or certainly a strong motivation for me to look at the third paradigm which we have introduced this morning, the intrinsic or loosely coupled in-situ visualization solution, whereby we transfer data to a set of concurrent compute resources where we have more leisure about more facility about using cycles and more memory available to deploy visualization. So I'm going to leave you with this message. I've demonstrated that I can interface a code with Ascent and ParaView in a very trivial manner with about 150 lines of code maximum to do a live connect, to do an in-situ and a live connection to a simulation. But as we grow up to scale with very tight memory budgets, perhaps the in-transit solution is something that we will predict. And with this, I will give you the following references. My slides. So at this particular address, you can download a copy of my PDF. Okay. And at this second particular link here, you have access to the Ascent tutorial to go into more details into some of the things I had to go through too quickly this morning. And with this, I thank you very much. I have one question here. Is the merging of decomposed domains done by ParaView-Catalyst on the fly? Or the code needs to be instrumented to do that before exposing data to Catalyst? I've read the question fully. In your experience, how difficult is it to instrument numerical solvers to make use of Catalyst? Okay, so the first part of the question is merging of decomposed domains done by ParaView on the fly. The answer is yes. The code is not responsible for describing to Catalyst how the data is decomposed. Okay, by definition, Catalyst will inherit all the data decomposition and all the parallel environment which the simulation uses. So there's no special code required to pass to Catalyst to describe the decomposed domains. And then as far as the difficulty to instrument numerical solvers, I think this of course would depend on each application domains. And what I have found is the most fruitful solution is to really work hands on hands with one of the code developer. This was my experience with the SPH EXA application. This is an effort of just a couple of days of work, okay, in my case. Guided by the person who developed the code, who knows the data organizations of the code in memory, and who knows which are the pointers to memory which are of importance to share to the in-situ visualization library, be it Ascent or be it Catalyst, I can very quickly set up that instrumentation. Please look on the, yes, on my slide, but also on the chat here. One of you has added the link to my, okay, those are the links to my slides, my PDF, but inside the code, I forgot on which page, you also have the link to my source code for the SPH EXA application. You have the source code for both the Ascent and the Catalyst port that I have done.